Lunch and get some more information here. I think we're going to get everybody come back in, seated. We're going to be on to our lunch with Ray's Kelso.
That's the statistical thing on farm.
Yeah.
And of course, we get into water purification, and that's a whole nother, and that's another problem. Right, please.
Everybody come in. John Metrick is the president of the North America Electric Drag Racing Association. As you know, I'm not a racer, but there are some preconditioned belief systems about electric vehicles that hinder their adoption. And one of them derives from the fact that most adults today, their main direct experience with electric vehicles comes from one of two sources. That is riding in a golf cart or riding in an elevator. As we know, things are a little different with a full-size car, and one of the most viscerally immediate demonstrations of the difference has, in the last 10 or 15 years, been by demonstrations on the racetrack, and the one that brings the point home the quickest is on the drag races. It's almost a cliche at this point, putting the electric car against the muscle car that has 4 times the horsepower, the peak horsepower, and simply leaving them in embarrassment. And that's done rather mightily, but it's very effective at bringing the point home. John is the president of the North America Drag Racing Association. I believe this is his 3rd electric vehicle convention, and he's kind of found common cause with us, and actually sort of runs our Sunday event that was really started out as a wine tour or something for people that were catching a later flight in the day, or just kind of went wind down on Sundays. But now we've actually, last year, made arrangements with a real equipped drag strip of 1/8 mile down around Sykes, and it was actually quite well received. So he's going to reprise that this year, and it's kind of getting to be a gig at Electric Vehicle Conversion Convention, and it's actually an INRA-sanctioned event. You can set records, and in fact we did in a couple of classes last year. He has a electric Miata, I think, at this point, isn't it? That is a world record holder in electric drag racing. And he's spent a number of years as a professional engineer, although mostly materials science, but applying those techniques to batteries and drive systems for electric vehicles. And there are some particularly subtle but quite powerful issues that you may probably would not encounter without taking performance to those extreme levels. And he's learned a lot of things along the way, and some of them I think are quite interesting. And he's agreed to kind of fill us in a little half session and show us what some of those are. Would you all please give a warm welcome to John Metrick.
That's when the levee breaks, but I love that one. My favorite band. And we're the little guy digging in the levee. And the levee is, of course, the automotive industry. I crashed my car a couple weeks ago doing Motor Week interview for PBS TV, and we got out of the car. It's my life project, you know, like a normal person would be crying. They strapped the blood pressure thing on me right away to make sure I was okay. 110/70. If you put a thing on me right now, I'd be probably 240 over. This is just as scary as me lining up on that drag race there the first day. Anyway, if anybody hasn't met me yet, my degree's in material science and solid state physics, and we just saw that video where it says solid state drive control. Did you see that? So I went into the University of Michigan. I'm going to be an electrical engineer. Long story short, finished a degree with a physics degree in the material science department, and solid state has to do with all those not quite metal, not quite oxide, that those semiconductors. And I didn't use that anywhere in my career. It's nestled as a little burr in my brain, like, what are we going to do someday to use my degree? But now it's coming to fruition, so it's kind of neat. Not what I thought, though. I'm going to do, this is part 3. I'm going to recap a couple drawings, sketches from last year, the ones I like, and then we're going to add a little bit of section on getting your electric motor torque to the ground. What are some of the aspects related to that? And I can't get this thing working. Do something. Oh, I just turned it off. Right button.
Turn the computer off.
I think I turned the computer off or something. Just a summary of conversions. You saw this already. Is that laser weapon here? Can I borrow that again?
Mm-hmm.
DC plasma 0 to 60 2.3 quarter mile. Best was 90, 155 miles an hour in the 1 mile, 134 and a half mile. Salt battery per calculated from Wall's racing calculator 0 to 60 in 1.5 seconds. The 0 to 100 4.0, 8.9 in the quarter miles our best run, and the figure I like is 266 kilometers per hour in under 1 kilometer. Doesn't that sound very impressive? And we've not run it on the 1 mile, but we think maybe 190 or 300 kilometers an hour would be a good target. They both have run with 2 War motors. DC plasma is sitting there kind of without batteries right now, but they're very similar in the motor situation, but the transmission was the big difference between the two. The underdrive with Arrow, and we have a 156 underdrive, and a 0.78 overdrive, and a 0.61 overdrive in this car. Of course, a lower gear number, much bigger tires in the Miata, and you can see a lot of video on YouTube at the channel called DC Plasma Racing. With most spaces in it. I like this chart. This was we went through, tried to pick out what performance level we want, 8, 9, 10, or 11 seconds in the quarter mile, and did all the weight difference and the volume difference, and took the chassis and said, if I'm going to have a 1,000-pound pack or 200-pound pack, how much would I need to get that down the quarter mile? Did all the calculations, and it spit up this table, and we ended up picking this, which was at the time the highest C rate we did was around 90 C. And then we derate that because that 90 C is really like a 1 to 2 second pulse number. It's not like a drag racing number. So, the pad cost around $9 grand to do that. These are cobalt, not the lithium iron phosphate. The recent technologies, we recycle some of the batteries, and we've been watching the chemistry. The net overall chemistry of metals in there is roughly the same as all cobalt. It seems to be the anode structure, the graphene nanoparticle, nanotubes, or whatever's in there, seems to be where the science is at. What makes these batteries have like less than 1 milliohm or resistance. They really get a lot like a capacitor. Long, flat, thin sheets, polymer sheet, another long, thin, flat sheet, and just multiple parallel sheets inside of there. So if you open up one of those cells, there's literally like 90 little foils in there. It's really like a 90P battery inside each one of those little pouches. I think what's going on is just these things are getting smaller and smaller, and much more like a little nano material science experiment. They predict we'll have 200 or 300 sheets and something about 2 or 3 millimeters. Other than rolling it around and making it around tube, I think it's getting darn near a capacitor. The batteries over the years, now from the design point to now, it's been about 4 years, and we started with 45C drag racing continuous 70C, and then we had a stint with 75 100C, and then the solid batteries got so this green one here, I'm sorry, the black one there is we're going to call it 100C, 150C drag racing continuous. That's over 4 years, and that's been the economically reasonably priced battery that you can just call on the phone and get some. That Moore's law is quite a curve from literally almost doubling in 4 years. These are some packs. This is a 1,000 horsepower pack here. It's an assault battery. This is a 1,000 horsepower pack. And this is a little 250 horsepower. It's on a motorcycle. And inside that pack, 250 horsepower, 2 contactors, a fuse, a shunt, and all the balance tap output lines. He loves it. He sent me a text and said, holy crap, holy crap, holy crap.
What's that in?
The motorcycle, Kawasaki, light speed motorcycle. I've been EMS free for 1.5 years. What was the second finger? Welcome, God, he said. So anyway, I can't completely disconnect from not monitoring all the cells, so it was one night, I think 3 in the morning, and I was watching one little weak cell and trying to get it back in line for the drag race in the morning. And I'm going, what the heck am I doing? My time is more valuable than this. I was super frustrated. And at the drag strip, it got like 30 minutes of turnaround. There's no battery balancing going on at the drag strip. You can shunt maybe a couple hundred milliamps, 200 milliamps, or 300 lithions, 250 milliamps, or Ryan's 100 milliamps, or 200, 300. It's not enough to draw down an unbalanced pack during the drag strip run, not to mention all the wires, components, and the weight of it. So we invented this thing. I sold about 10 of them. I call this the BBS, basically battery balancing system. It's a 300 volt military appliance wiring, voltage spec, D-sub pinout balancer, and the dischargers in a box. And so when you're in between drag race runs, I come over and I plug this thing in, and it reads out all, say, 36 cells, and I can see the high and low, super simple. Could unplug it and go racing, and then I can, with a clear conscience, say that it was healthy. And in the middle of the drag race run, I am not lifting my foot off because my BMS says, "Oh, I got a low cell in there," you know. So I wasn't, I had to defeat all the BMS issues. So I really like to move the BMS out of the lexicon, and we need something else. So this is my attempt at that's a BBS. And if you don't want it inside your box, like that's mounted, you can mount it on the outside of the box here. With just a cable wire going in there. And then top balance and bottom, or bottom balance with this, you know, racing, we always want a top balance. Long story. I brought this diagram back to the power, voltage, current diagram. This is a controller current limit. Up here at the top, 2,000 amps. This is the lowest voltage it can go, 700 volts, and the highest voltage go 400 volts. So the biggest battery pack that you can put in there and meet the specs is a 333 volt pack nominal, 348 volt nominal per the Zilla controller, and 375 volt charge number. That's the recommended. So in this, you can see the world of what that controller can do. And then if you have your battery discharge curve, you can lay that on here. It's that S curve convolution. You know, if you raise the current, it drops off voltage, and multiply the voltage times current, that's your power. So anyway, that's what this is here. Each battery has got a curve, and then you lay that on top of your controller, and you see how your battery pack matches to your controller. And it's good to get just a quick reference. You can see, oh, they're lined up or not lined up. Like if I was way off the top there, I would need another controller. I might want to go down in voltage or up in voltage. And finally, if you're buying the pack and you've got this controller in mind, you've got performance level in mind, what S number do I go with and what P number do I go with? We can line out the P number over here, parallel, and then series number here. Boom, 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 boom. Pick your controller. You want one Zilla 2, you want the Shiva Epinetics. You can see whether you're matched well or not for your controller. Just want to put extra money in and have over capacity or less capacity for coming short really happy. So those are from last year. This is a typical run chart for drag racing. This is from DC Platinum. This is a 11 to 1200 amp motor run. And the blue line here is the horsepower, which is right over there. And you see that it took longer to reach its peak, and then you hit the EMF limit of the motor, and then it drops for the rest. This is a single speed run. And then I raise the controller settings to 1500, 1600, and it goes up a little bit higher, but then it hits that point and it comes right back down to the same EMF limit. And this got me thinking about, what? We're spending a lot of time without putting out the peak horsepower, so all my calculations, you know, how many horsepower you have in your system, you're not really making that, but it's a tiny little fraction of your, your trip to the highway speed, somewhere 30 to 40 miles an hour. This is DC motor pilot. So it's really about making more horsepower across the whole period of time that you're on the track. This is another chart from last year. This is a simulated dyno from 2 Warp 9s. And you really need to have your dyno information. I'd never run on a dyno. Couldn't get one. The NetBeam website's got some inverted kind of curve. It wasn't useful. So this I use pretty regularly. And how do you build one of these? You have to know a couple of points. You got to know kind of your pack power level, max. You got to know your torque number, and from your torque and your RPM, you know your horsepower, and then you need to know this EMF curve shape. How does the motor voltage affect this dyno chart? If you have a 140 volt brush system, you're here, and here. And if you can upgrade to the Hellwig carbon brush system that we use, we started using 170 and 190, and 199, and 200, and 210. And we're not seeing damage on the brushes. We're not seeing damage to the system. We've got a few tricks Tom taught us about spring pressure on the brush, and obviously we're running 1700 amps. But you can see if I just tickle the throttle at 150 miles an hour, it's not making a huge fireball. It's the current that's doing that. The heat comes from I squared R resistance at that brush tip, so we don't think we see a problem with 190 volts and low current. What's the dyno look like if you have a pack limit or a controller limit? You come up and you hit this pack limit of 400 horsepower battery pack, and you keep making it, and keep making it, and keep making it until you hit the EMF limit, and then it falls. And you see that's very flat. So I've talked to a lot of people that say, yeah, I'm pulling all the way through the quarter mile. You are pulling all the way through the quarter mile. But there is an EMF curve. You most likely hit it at some point. The impulse motor is a little higher than the workman motor. But if you had a bigger pack and a bigger system, you can actually drive this peak up a little higher. And if you theoretically had a 900 horsepower motor controller that could take it, we theoretically think that that would be the curve. So there'd be this flat and stop and a peak like that. You just haven't been able to put 900 horsepower out, out of two motors. Shifting from that, now the dyno, and I've got all this torque and I've got all this power, the forces affecting your EV's performance, okay? On a load diagram here, we've got 4 forces acting on your car. There's also wind and various side loads and things like that. But your earth is pushing up on your car at all times. The atoms aren't compressing, so it's pushing up. You have your weight of your car pushing down. As you are moving forward, you have forces that are pushing back on the car, which are the aerodynamic drag and your tire drag. And of course, your motors through the transmission and the drive shaft, differential, axle, wheel to the rubber, has to overcome the forces of aero drag and tire drag, and then any act left over that you have after that turns into acceleration. And that difference in force between the aero forces and the amount that you're making divided by your weight of your car is your acceleration. So just talk a little bit about aero drag and tire drag. There's a fellow who built the long R&D experiment. This, this very long car, the fiberglass thing. Is he here? Yeah. So it's like an experiment in aerodynamic drag race. It's got a very, very long tail, and CD, you think it might take you over like 0.1 or some crazy. So just quickly, I'm not going to read everything to you, but coefficient of drag, CD, frontal area A, speed V, force of the aero drag, I call that drag in newtons, and your F drag is just your coefficient times the square of your frontal area times your velocity. Tire drag, we got from a reference table for a car with weight N, the variable W, you multiply that drag factor times the W, and then you add both the force from the tire drag and the force from the aero drag, and you multiply by your velocity, and you get the power loss in Newton meters per second. And a couple of equations there to calculate that into whatever you want, horsepower or kilowatts. And then an interesting thing there is if you're only doing 20 miles an hour, that's your goal. It could be a science experiment where they're going around a circle track. What should you be really worried about in your car? The percent of these things working against your car at 20 miles an hour strongly related to your tire drag. Aerodynamic drag, a whole lot less. At 20 miles an hour, a 20 mile an hour wind will double your drag. So there is other issues like wind. But now let's take it to 165 miles an hour. You see that the percent contribution of tire drag to the total almost minimal. I mean, it's 10% in there. It's interesting, but you know, trying to fix tire drag and do compounds and things that you like. Your choices are very limited in a tire. So it's really mainly all about aerodynamic drag when you're at that kind of speed. That chart was for my Miata with a certain CV in front of it. What does total drag look like? Here's a table. We calculate the miles per hour, horsepower of drag. You've got to overcome. Again, for Miata. And the table. And then this is the chart related to that. Ryan said 10 horsepower for 30 miles an hour. You can compare with it. It's just what the thing comes up with. But he also did a drivetrain and a couple other things. But it's a very low number. However, you take that up to 165 miles an hour, and you need 300 horsepower just to maintain that speed. Several people have called, heard me to calculate what it would take to do 200 miles an hour supercar. And I said, well, if you have something similar to this, like a Corvette or whatever, you're talking about 600 horsepower just to maintain that speed, not accelerate, just to maintain the speed. And that's why when you see sevens and all that have top speed about 212, but that motor can only do, 600 something horsepower. So those two come together, that's where you get that top speed from. G-force now is a function of applying your extra horsepower minus the drag horsepower to your gearing. And in EVCON, we're contemplating going to multiple overdrives, and this is your G-force on a 2,900 pound car with a 26-inch tire with 3 different gear ratios. And you can see at 60 miles an hour, we were at 1.5 Gs. That's really breaking the tires loose on the concrete. So the seat of pants dyno was we could spin the tires up to about 60 miles an hour. Very dangerous.
Yeah.
And it was right on. I couldn't believe it. This number here, this G-force, is you're going to see later a little bit of coefficient of friction on the tire. What can your tire grip the ground with without breaking loose? You change to an overdrive gear, or second overdrive gear, you see that rather than not having the overdrive gear, you were at, say, a G-force of 0.5 by adding the overdrive gears, and no other change, you've gone to a G-force of 0.75 or 50% more acceleration by just having that extra gear. On a time budget. This is a little table. You put your tire diameter in, your drive ratio, and then you can see whether or not you're inside that PVI diagram that your system can put out. And then my little spreadsheet highlights whether or not you're inside the table or outside the table, so you can decide whether or not you want the gear to do your speed that you're targeting. Why is this not correct? I'm going to just bear with me a minute. Any questions?
Yeah, all those charts, are those like actual empirical data or theoretical?
Almost all of it's empirical.
Thanks.
Some of them were theoretical, and battery information and all that, that was all empirical. Empirical meaning
Real world, I think that's what that word meant. I'm trying to be smart.
Just takes a few. It must be like a Rev 1 and a Rev 2. I just got 2 slides. This is really close.
Looks train too hard is all the time.
Right.
Mm.
Must be yeah, 12 o'clock p.m. Sorry, guys. Shoot. Misclicks.
John, I had a quick one.
Yes.
This is Dennis.
Yes.
You talked about derating the 150C pouches. About how much do you have to knock those back?
25 seat.
Okay.
So the 200, we're gonna derate 50 seat, so about 1/3. Okay, well, I'm gonna just jump to the conclusions.
John, in
Yes.
that mile run, how hot these motors, I mean, what kind of thermal limit? Hold it wide open or whatever,
The motors
to run
on
mile?
track, the mile, to run the mile.
Probably get into the heat, everything, moving down.
Yeah, everything, I just detune the system so that it kind of gets the maximum temperatures on the motor, the con, and the controller, and the batteries kind of all at the same time. But we ran into control of water issues due to the fact I'm only running like 1 quart of water in that car. The water temperature got too high. Real quick, 5 minutes.
All right.
Chassis equations 1. I'm not going to read out because I'm on a time budget, but Newton's second law, F equals ma, translates into tire grip weight times the coefficient of friction. The mu of the coefficient of friction times the weight governs everything in a traction limited situation. If you're traction limited and you're trying to go faster, this is the equation that you have to meet, not some kind of torque or gear or anything like that. It's about that coefficient of friction and the weight that you're putting down onto the drive surface, the contact patch it's called. Acceleration is the coefficient of friction times the contact patch weight divided by the mass of your car. Blew my mind. I couldn't believe it. This is right out of Jerry Cole and Chassis 101, and it turns out all my stuff about gearing and all that stuff's interesting, but in the traction limited acceleration, this is the equation that governs, not the other stuff. Chassis friction. So, how do you get more friction, more grip? You can put a bigger tire on. This is a 24-inch Corvette tire that we had on the Miata when I bought it, and this is the tire that's on the Miata right now. The actual Miata tire was like a donut next to these things. Concrete friction 0.8 roughly on a good track. Asphalt 1.2, and then a VHT spray drag strip with gummy tire you can get to 2.2, 2.5, 3.0. Cheapest, absolute best way to accelerate when you have traction limit is to put yourself into some good tires. Chassis dynamics. The W is the weight of the contact patch. The weight of the contact patch is dynamic. As you accelerate, in this case, for example, you're turning your differential this way, and your springs are counteracting that. You end up with this torque on your chassis, so you end up with different weights on the left and the right side. The next best thing in a traction limited situation is to put in a locker or a spool in your rear end. You even that out. You take away the chassis reaction, changing what drive tire is governing it. Because without the locker, your weakest tire governs your situation. So here's some equations for that. I won't go into that. One thing is we learned was an EV with a motor that big doing 800 horsepower and a big block aluminum V8 with a supercharger on the top, 4 feet, 6 feet tall, humongous thing. The motor, in fact, the rotor weight doesn't even count for the momentum part. You have a very, what's called high central tendency of your weight. The chassis just turns. The guy who built the chassis looked at the video from our car, and video is very important. He just says, your car is behaving like it's got 3,000 horsepower. And he says, that car chassis is good for that, but you need to take some reactions. You need to preload your car with a whole bunch of extra weight on the left, so when that thing starts to go, the spring doesn't bottom out. And we literally were lifting the front left wheel off the ground, and for 4 or 5 months I thought, mealy, yeah, mealy. Corvette Horsepower TV filmed us, and he took it from the right side because he was right in the starter position. Nobody's allowed there usually. And the video shows we were cramming the right tire down, and I thought, holy mackerel, we're not wheeling it at all. We're just twisting the entire chassis, the super stiff 25-2 chassis. We readjusted or rebalanced it. Huge difference. We weren't swirling anymore. We weren't pirouetting. We'd go up on one tire, and the car would want to right to the other lane. The huge thing about EVs, almost no like outside weight. In addition, our entire battery is inside at 18-inch wide and about 18-inch tall. So I don't have any weight, kind of in the front or the back or the corners or stuffed in the trunk somewhere. So the car just overall, you have all these factors going on. Locking differential equation there, open differential equation here. Much more complicated with an open differential situation. Roll, stiffness, and chassis, blah, blah, blah. I know we're in speed here. You plug all those equations in and you get a chassis reaction table. You can play with the changing of the weight, changing the center of gravity, raising the center of gravity of the tires. And these are conclusions. Changing weight of your car has almost no effect during the traction limited aspect. It doesn't come into those equations at all, the weight of the car. If you have a traction limited situation, your force times your forward force times the weight of your car is a function of the coefficient times the weight of your car. So as you reduce the weight of your car, you're reducing the force going forward on your car. So during that period of traction limit, changing weight of your car wasn't something as a solution to fix that. Blew my mind. Shifting the weight to the back has a moderate effect. More weight in the back to put more weight down on the rear wheels if it's a rear-wheel drive car. Moderate effect. Installing a locking differential spool, very big effect. Locking them together and taking out the action of the weakest tire being the drive tire has a big effect. Blew my mind. Raising the car's vertical center of gravity, making the car taller, because I wanted to slam me out. I wanted it low. I wanted to corner and be real cool. We ended up raising the car 2 inches all the way around. It was like night and day. The car got up, lifted both the tires up, it felt different. People came over and said, "Do you know you just did a wheelie for 50 feet?" That's that difference of that vertical center of gravity shifting the weight to the back without changing any weight of the car. And the biggest thing is improving the tire and track grip is the biggest bang for the buck. Bang for the buck. I'm doing this late last time. Other items, contact pads, tire dynamic, tire combo, weight distribution, suspension preload, center of gravity, power density, and looks. If you want your car to look a specific way, that's your thing that's your design parameter. It may not work with the drag car or race car or whatever. This is a little picture of 1,000 horsepower. It's a suitcase. We take all that stuff we've learned, we put it into some custom drag racing modeling software that we were able to give your G-force at any spot, 0 to 60 time, top speed, 1 mile speed. I call this learning to drive. You guys got 3-speed transmission, starts in second, then third, then fourth. This is a picture of shifting way too early. He never uses the full horsepower in that pack. Does everybody see that? No, right? The blue dot is the horsepower, and he's shifting before he reaches the peak, so that car has a lot more potential. This is one done a lot better. This is Dave Carter, he had a Porsche, and he's, for his NICAD pack, it's about as good as he could do. He could maybe shift a little bit earlier, but you learn a lot by taking data. Everybody learn to take data, please. This is not how you do it. This is salted battery. First time I ever got the noise issue worked out on the data acquisition system. I didn't put the accelerator all the way down. I spun the tires. I then shifted into second, huge amount of kick in the ass, and then spun the tires, got off the throttle, was sideways, got completely off the throttle, realigned myself, put my foot down on the accelerator again, and then was so nervous I waited until it was like 120 miles an hour, then shifted into fourth. Not that you do it, but put your run back together, and you're pretty calm about what happened. So our best run to date, plotted on top of some old DC plasma runs, we've hit a peak of 990 battery horsepower. It's not rear wheel horsepower. The dyno's coming, right? Oh, yeah. No, I can't dyno. Two years ago, I brought that thing up there. I'm not sure what you guys thought of me. I hope that someday one of you guys becomes really rich inventing something so I can borrow money from you. I didn't know what to think. This is what I thought. So I built this thing, and everybody said, oh, it's so long. Well, here's a picture of it next to a power line without an overdrive, let alone 2 overdrives. It wasn't that long. Cutting it. I'll mention here that I think kind of the version of the future I'd like to see would be something like that motor on the left there, something with a center hollow core with a spline axle all the way down through 4 motors, each doing, say, a quarter of a megawatt. This is an inline reverser there. That's it. Thanks. Okay.
Thank you, John. A couple of quick announcements. Apparently, Brain has just completed the first drive of the electric car. He's hoping Brain Seymour will stop by the shop and tune it up for him a little bit. We have lunch today, courtesy of Ray's and Kelso, and it commences now. And we'll be back here at 1 o'clock.